Hello wonderful person, this is Anton, and in today's video we're going to be discussing this beautiful system of TRAPPIST-1 once again and talking about, well, this one really difficult but simple concept of what makes it so stable and why do these planets actually go around this beautiful star in such precision. Anyway, let's talk about what's known as resonance, and welcome to What the Math. So why exactly are we talking about this? Well, one of the main reasons is because normally, if you have so many planets close together and a star in the middle and planets are relatively large, it's very, very difficult to actually create such a stable system. Let me show you an example. Let's just randomly create a system with a star in the middle and place a few random planets around it. Okay, some of them actually already fell apart. And just kind of run the simulation for a little bit just to see what happens. So you may notice that it's not really visible yet. Now let me actually just delete the fragments here because this will cause the game to be too slow. We might actually need to place more planets on the outskirts because they're actually warming up a little bit too fast. And so here I had to just change the system a little bit to make it run a little bit faster. And so here you go. As you can see, some of these orbits are already shifting around and are moving closer or farther apart, and at some point the system might actually kind of fall apart. And when the scientists ran the simulations for TRAPPIST-1, this is exactly what started happening, and they actually started thinking, well, how can the system stay so stable? So what they did was this. First of all, they took a look at it and thought, well, maybe it is actually in the process of transition and planets might actually collide soon, and maybe it is that one random chance of seeing the star system where things are just shifting around and moving around. But unfortunately, if you look at the timescales of normal solar systems and the chance of encountering such an event, it's almost impossible. It's actually so tremendously minuscule that the scientists started thinking, well, maybe there is something else going on. And what they started doing is they started counting how many orbits each of these planets makes around the star in a certain period of time. And what they realized was really remarkable. It's something that we've discovered a long time ago in many different other systems, like, for example, Gliese 876 and Kepler 223. And we might even have these actually here. And there's a Gliese system. And what we discovered was what's known as the planetary resonance. And basically here, specifically in this system, for every one orbit of the farther system, the closer farther planet, the closer planet makes 2 orbits, and the closest planet makes 1 orbit, and this one makes like a lot of orbits. And they all basically kind of connect in this very unusual pattern of resonance, which is basically a pattern of orbits. Now we also have these around most satellites in our solar system. We have these around some of the planets as well. And what was remarkable about TRAPPIST was that this was the biggest resonance we've ever seen in astronomy. This is actually the longest resonance we've seen in terms of the actual number. So here, for 1 orbit of the farthest planet, or actually not for 1, but for 2 orbits of the outermost planet, which is TRAPPIST-1H, the next planet makes 3 orbits, this planet makes 4 orbits, this one makes 6 orbits, then it's 9, 15, and the last one, the closest planet, makes 24. In other words, every 2 orbits of this one makes 24 orbits, or every 1 orbit of this one makes 12 orbits. Now, this kind of a resonance is what keeps these planets from colliding. They basically keep each other in check through gravitational interactions, which are very, very common in astronomy. And achieving such resonance, well, it is by chance, but it is kind of difficult. And what's really interesting about TRAPPIST-1 is that because the planets are so close together, because they're so massive, this is actually the only way for them to survive for such a tremendously long time. Now, that's not all I wanted to talk about. I actually wanted to show you a simulation that helps you visualize, or not visualize, but hear this resonance in a little bit more detail. And this is a simulation by Canadian scientists. You can learn more about them by going to the website that I posted in the description below. But basically, it kind of looks like this, and it's called TRAPPIST sounds. They actually simulate it in many different ways, including a YouTube video. But we're actually going to play this resonance directly by using the little app they created on the website. So here you can actually add the melodies from each of the planets by adding them individually. And the reason they added this kind of simulation is because, well, they realized that scaling system orbits into tones actually makes a lot of sense for human mind, and this repetitive pattern is very easy to represent in terms of music. So every time a planet passes a certain point, it makes a different tone. And when two planets come close to each other, they make a drum beat. So if you can think of this in terms of music, you could actually create quite an interesting melody for each of the systems and each of the solar systems that we discover by using this type of technique. And this is actually very, very brilliant and super fun. So this is, I believe, was created by a person by the name of Matt Russo, and he created this musical representation where we can basically just play this. Okay, so I'm going to slow down tempo here because it is going to get pretty loud, but this is actually really cool and really brilliant when you think about it. So representing solar systems with this type of musical interaction can actually maybe help us navigate the stars in the future and help us understand where we are, and most importantly, give us an idea of how to better define solar systems. So this is a pretty cool simulation. There's another one for Saturn as well, and Saturn moons and their resonances. But we definitely have these everywhere in space, and creating music out of it definitely adds a little bit of a new note, pardon the pun, for this type of a field. Anyway, so that's all I wanted to talk about in this video. I wanted to show you the simulation, talk about the resonance of TRAPPIST-1, and give you an idea where you can learn more about it by basically visiting this website. Anyway, thank you for watching, subscribe if you still haven't, share this video with someone who enjoys watching space videos, and come back tomorrow to learn something else. Let's go back to Universe Sandbox and finish the simulation with a loud bang at the end. I'll see you guys tomorrow. Space out, and as always, bye bye.